lecture. Okay, so we will finish this chapter and then hopefully talk a little bit about the representation learning. Okay, um, and next lecture we are going to talk about the autoencoder. Okay, um, that's about it for this semester. Okay. Um, and so the week after next is going to be the final exam. Okay. And one thing to tell you guys is that, okay, the department actually has an announcement to make. Okay. Uh, um, and because they want to reach as many vocational students as possible, and this is not for you guys. Okay, it's for night class. Okay, for night session. So never mind. Okay, but okay. So the week after next is going to be the final exam, and then the third lecture. Okay, from today is going to be the project presentation, okay, for the final term project. And for that day, okay, the TA is going to, randomly decide an order, okay, for your presentation, okay. So the TA will announce the order a week, at least a week prior to that day. Okay, and each presentation is going to take maybe, because in the afternoon session it's going to be quite a few groups. So we will see each presentation. I mean, it's going to be maybe between 10 to 15 minutes, depending on how much I mean, we will decide about the length of the presentation, okay, and announce that maybe through the class, and during that day, okay, we will provide a pizza, okay, for you guys, okay, as usual, okay. So you guys are more than welcome to come a little bit early, like around 12:30, okay, to enjoy the pizza, okay, before your presentation, okay? And some students asked me about the final exam. I mean, is it okay to bring one-page cheat sheet, okay? Yes, okay, you guys are allowed to bring one page, A4, okay, cheat sheet, okay. Whatever you wrote on that page, okay, I don't care, okay. But it's not going to be a whole book, okay, just one page, okay. And I think everything remains remains the same, just what we, how I told this class last time, okay. So hopefully you guys have a better understanding. And already, by the way, I already have the sample final uploaded to the EE class, okay. So just in case if you don't know the format of the final exam, please go check it out, okay. We normally provide a little bit more questions than required, okay, so that you can have a little bit of wiggling room, okay, you can drop one or two questions, in your final exam, okay. Hopefully, this is going to help you to get a better grade, okay. So, okay, so back to our lecture, okay. So last time we talked about the RMN, right? And we actually create a model that is used to predict like the time series data, okay? Originally, we want to create, we want to predict like just one time step, okay? But later on, we say, okay, now we want to predict like 10 time steps, okay? Then, okay, we found that if you apply like the model that predict like the next time step 10 times for those 10, additional time steps, it's going to, the performance is going to be very poor because like the error actually gets accumulated. So what we can do is that we can, convert, we change the model so that it predict like the next 10 time step, like together, okay, just in one prediction. This way you avoid like the issue of like error accumulation, okay. So yes, so the performance, okay, if you use that this model, yes, it's going to perform much better than using like the original model to do like a prediction 10 times. Okay, but actually, okay, you can even you can actually like convert, because the previous models that we talked about, okay, they are all like sequence to vector models. Okay, so we can actually convert this sequence, our sequence to vector model into sequence to sequence model. So what is the difference? Okay, in the sequence to sequence model is something like this. Okay, yeah. Instead of training the model to forecast the next 10 value only at the very last time step, okay, we actually, in the sequence to sequence, we train it to forecast the next 10 value at each and every time step. So it's going to be something like that. Okay, you get the first 10 steps, first 10 values, and use that to predict the next 10 values. And then, okay, you move one step ahead. Okay, so say like, okay, say this is like, okay, so this is the first 10. So you are going to, your model is going to use these first 10 values to predict the next 10 values. Okay? And then, okay, your model is going to move one step. Okay? So the next is going to be something like this. From the second element to the 11th. Okay, so this is going to be the next sequence. Okay, the second next 10 element, and you use that to predict like from here to one more element. Okay, something like that. Okay, so you predict this. You use this to predict this one, and then you move one step and you predict next 10, and so on. Okay, so that's the idea. Okay, so basically, okay, the advantage of this technique, okay, the loss will contain a term for the output of the ion at each and every time step, because now, okay, originally you use the whole sequence, and then you only account for the last output, the loss, okay, only accounts for the last output, okay? But now, because, okay, for every, like, for example, from here, you predict the next time step, and you can use this to compare with the ground truth, well, for the loss, and you can use that, I mean, to fix, I mean, to get the gradient to fix your model, okay, to improve your model. So you get a lot of error gradient, okay, compared with the original approach, okay? So, yeah, so because you get a lot of gradient, I mean, in flowing through the model, so this gradient will both stabilize and speed up training. So what do we do, okay? The first thing we need to do, obviously, is to prepare our data so that, like, we take the first 10 and then predict the next 10 and so on, okay? But actually, what we do is, you know, not exactly like this. We are going to create what we call a causal model, okay? So it's not like you use first 10 to predict the next 10. We are going to use the first 10 to predict, to predict like this from first 10. This is the first 10, okay? And then we want to predict here, from here to from the second element to the 11th. So there's we only predict like one additional element in this round. Okay, and then we move up from the second element to the 11th. We predict like the third one to the third one to the 12th element. So every round we only predict one more. Okay, and the reason this is called the causal model is because like you can see, you know, in this case, okay, because you use the first 10 elements, and you predict like from the second element to the last one plus a new element. So some part of the input somehow overlap with the output, right? So that is why this is called the causal model. There's overlap between your X train and Y train. X train is your input. Y train is your ground truth. Okay. So what you need to do is here. Okay. You need to prepare your data accordingly. Okay. You have your X train ready and you have your Y train ready. Okay. And then after that, okay, you also need to change the model. Okay. Remember, now it's a sequence to sequence, right? So your input obviously is still, I mean, it's a set. It's just a sequence. Okay. But the output is going to be a sequence. So remember, like originally, okay, these two lines remains the same. Okay, we have like a simple argument. Okay, return sequence equal to true, okay, and this part is the same. However, here, okay, originally we used like just the dense layer with 10 elements, right? With 10 neurons. But now, okay, because we want to convert it into the sequence, so we can wrap this layer by the time distributed, okay, so that we make the last, make the output a sequence as well, okay. So this time distributed is going to convert the output into the shape of the sequence, okay. So, supposedly, if you use the dense layer and and train it using like the sequence to sequence, I mean, it's supposed to work as well, okay? But the reason to add the time distributed dense, okay, to wrap this dense layer with the time distributed is to make it more verbose, that you want this output to be sequenced, which is normally a better practice because because dense, I mean, can be used for both, for either the vector output or sequence output. But I mean, you know, if you don't wrap it with the time distributed, you know, we don't know what type of model we are doing here. So it is a better idea to make it more verbose. Okay, make it like obvious. Okay, here we are dealing with a sequence to sequence model. Okay, and then there's one small tiny detail that we do need to be careful. Okay, yeah, we train it like everything looks just right, but there's one thing. Okay, because now remember, every time we use this 10, the first 10, and we predict the next, well, the window that shift like one element. We predict that, and then and so on. So, but yes, I mean, this is going to be used for training, but for evaluation, I mean, when it comes to evaluating the model, the only thing that matters is because eventually, say we have like the first 50 element.